Heating with the wind. Now, what the hell do I mean by that? Heating with the wind, not to be confused with pissing into the wind. That might heat you for a few seconds and then you'll be very cold after that. All joking aside, let's say you live out somewhere in a rural area and you say, oh, I got a lot of wind here. It's really windy, you know, out on the plains or wherever you might be. And I want to use that wind to heat my house. How could I do that? All right. Now the obvious answer to that here in 2021 is you put up a wind turbine, you generate electricity, and you use the electricity to heat your house and however you want to do it. Okay, that's the obvious way to heat a building with wind. And but I'm going to go over a little bit more obscure, older methods that people have proposed for doing this. And they're very interesting from an engineering standpoint, but at the end of the day, if I said I have to heat my house with wind and I'm going to build it and do that, I'm going to be generating electricity on the wind turbine and I'm going to be using that to heat the building. So, but what if electricity just disappeared tomorrow and it wasn't available to us? How could we do this? All right, so there's a couple different ideas that people have had, and what's inspired me about this is there's this website online on the internet called Permies, basically permaculture. So it's kind of people who are very much into a back to the land sort of version of dealing with environmental problems. It's what you might call dark green environmentalism. So it's a little bit less technology oriented and more tradition oriented. And that is kind of the perfect breeding ground for this whole idea of heating with wind in non-electrical, using non-electrical technology. So there's a forum thread on there where these guys get into a conversation about, I say guys because more than likely they're mostly men typically. You know how it goes, right? With this kind of stuff sometimes. But the whole thing started with, I know I can put up a wind turbine and generate electricity up there and bring it down and use it to run resistance heaters. But that's so inefficient, and so inefficient was capitalized on the forum thread because, and it makes me laugh because the whole idea of electric heat being inefficient is really not anything that is a part of the physics of it, but more of the economics of how we human beings have decided we're going to generate electricity. So the ways that we decide we're going to generate it have resulted in the electricity from the power grid being more expensive than just burning the fuel directly. Hence the reason there's this social idea of electric heat being inefficient. It's more expensive than alternatives, but it's not necessarily inefficient as much as the vision is, especially if you're using something like a wind turbine to generate it. So these guys on the forum post, they proposed, okay, we want to not use electricity because electricity is supposedly inefficient. I'm kind of like thinking it's like, oh, this idea that's in people's brains. It's inefficient, so we're not going to use it. We're going to use something else to turn our wind power into heat. So their idea, and it kind of morphed into, obviously people started doing research and things like that, and it morphed into various concepts. But the first idea was, okay, we know that we could take that wind turbine rotor and use it to turn, let's say, a brake disc, like a car brake disc, a metal wheel that's got friction pads against it that turns the mechanical energy into thermal energy and heats up the brake disc. And then their idea was, okay, you submerge that brake disc in water. All right. So you got a tank with water in it, proposedly at the top of a wind turbine tower, lattice tower, whatever it might be. You got your shaft of your wind turbine coming in here. You got your wind turbine blades. All right, big wind turbine blades. And your shaft, and you got a brake disc attached to this shaft. And there's water in the tank. Okay, and they were going to clamp brake pads, a brake caliper, and clamp that brake disc. And then that would create friction right in here as the wind turbine turns. Obviously, you have to have a mechanism to adjust the brake pressure based on wind speed, but they would basically be creating heat, and then the heat would be transferred to the water, and then the water would go down to your building, and then the heat would be used in the building. So it's like, okay, yeah, that would work, you know. It's got a lot of technical issues, but it would work. How can we simplify that? All right, instead of having a carved brake disc in there that relies on solid to solid friction, what if you just installed a smaller wind turbine inside the tank? All right, so we're gonna spin. The air is gonna turn our big wind turbine blades outside of here, and it's gonna run this little propeller inside the tank, and the water is just gonna slosh around inside this tank. All right. You know, this could be shaped however. It could be like a paddle wheel. It could be like a pump impeller. It could be like a fan blade. There's a lot of ways you could do it. But ultimately what's going on is you're creating fluid turbulence inside this tank because you're taking that mechanical energy and you're just spinning that blade inside of a almost static tank of water. You only have a small flow coming in and a small flow going out, and that mechanical energy is dissipated because that water is churning inside the tank. It turns it into heat and heats the water up. Ironically, this is nowhere near a new idea. Back when, so the SI metric unit of heat, or energy I should say, is the joule. Joule, James Prescott Joule, I think he was English, back in 18th or 19th century, I don't know when it was, but this is like physics 101 when you take physics in college and you talk about energy. How do we define the unit of the joule? And a device like this was how Joule did that, but instead of having a wind turbine rotor attached to the shaft, he just had a pulley wheel with a string and a 1 kilogram weight on it, or some weight. And the whole idea was the weight would fall a specific distance. It would turn the rotor inside the tank, and the energy of that gravitational potential energy of that weight going down would be turned into heat inside this tank. And then he measured the temperature using a thermometer, and he knew the mass of the water in the tank. Basically, this is what they call a calorimeter, and converted the gravitational potential energy of the weight into thermal energy, which was then measured. And the Joule basically said that they call it the mechanical equivalent of heat. That mechanical energy can be converted directly to a thermal energy, and they're the same quantity. And we're basically scaling up the Joule device with this wind turbine that's going to heat up water. All right, and it's very, to somebody who's into permaculture and back to the land sort of ideals, this is an elegant idea, because it's shunning modern technology. And when I say modern technology, I'm talking about electricity and electronics. Even though electricity without the electronics is relatively basic, it's pretty simple. Um, it's still this psychological concept of something that's totally mechanical or hydromechanical or whatever you want to call this. You know, and there's ways that you can make this tank and stuff up here a lot more compact. So you got to build this at the top of a wind turbine tower. That's a big problem. So we have our tower. We're just going to use a lattice tower, like the old days on the farms when they had the wind turbines to pump the windmills, to pump the water. They used lattice towers, and the way that those devices operated is they had the wind turbine shaft came in here, and it drove a crankshaft, probably through a gear reduction or something like that. There was a crankshaft, and the crankshaft went to a rod that went down into the ground 100 feet down or however deep the well was, and it pumped that crankshaft up and down, and it pumped the water out with a reciprocating pump. So the wind power was actually transmitted mechanically all the way into the well. But what we could do here, you could transmit it mechanically. It probably would be okay to do that. But the proposal with this there's an article that they found on this forum post from like the 70s. I guess over in Denmark, they built a big wind turbine there in the 70s. They had what they called a water break dynamometer at the top of the tower. So that's just basically, think of like a water pump, you know, a centrifugal pump driven by a motor. Instead of using an electric motor to drive the pump, you're using a wind turbine rotor. And the pump is set up so that the impeller that's inside this pump intentionally creates a lot of turbulence. So it's designed to make heat more so than pump the water. But it did in fact pump the water. So it was a combination of a pump and a heater, mechanical heater, whatever the right term for that is. So they ran their water lines, a supply line and a return line, up and down the wind turbine tower. These towers could be hundreds of feet tall. And this was a closed loop system, and it had to be closed loop in order to have the pump at the top of the tower. So you got to pressurize it enough so that the gravitational difference in height of this tower, you weren't going to get issues with pumping the water that height. Because normally you cannot have a pump that's elevated more than, say, 30 feet off the ground, or else the water will begin to boil inside the pipeline. Or the atmosphere just can't push it, so it just turns to vapor, and you end up sucking vapor, assuming your pump can actually draw a vacuum. A lot of them can't. So we're pumping our water in a closed loop, and we have our rotor that basically converts some of the energy into pumping power, but the vast majority of it gets turned into heat through just stirring action. So an experiment you could do in your house, you know, if you have a blender in your kitchen, take some water, put it in the blender, and run the blender for a few minutes. And then put your finger in the water and see if it warmed up. And it should have warmed up, because you're agitating that water and you're creating massive turbulence in that volume of water, and the mechanical energy being put into the blender's blades is being dissipated as heat in the volume of water, the same way we're doing here, the same way that Joule did back in the hundreds of years ago. So we got our water loop, and this process is pretty good. I mean, that the mechanical energy, the foot-pounds of torque, you know, the actual power on the shaft that the wind is producing is being basically converted into heat at 100% efficiency when you measure it right here at the top of the tower. Now, if this is so simple and so elegant, why are people not doing it? Why is it that all the big wind turbines that you see for sale for residential use or whatever just generate electricity? There's a lot of very good reasons for why this isn't being done. Probably the biggest problem that I see is this is obviously something you're only going to do in a cold climate. So what happens in a cold climate to water? All right, it freezes. So this water in this system, you have to make sure it doesn't freeze, or else it will basically stop working, possibly even cause damage to the whole entire system, either to the piping or to the water break rotor at the top of the tower. Okay, so you got that problem, freezing. Okay, you can just add some antifreeze to the water, right? And that'll solve the issue, correct? So antifreeze is good stuff, but it also reduces heat transfer, which increases the amount of water you have to move through the lines. And it's something that chemically it can break down if it gets overheated. Antifreeze, it's okay, but it's not ideal. And for anybody if you're into permaculture and you want to put ethylene glycol or something like that into your system, you're worried about environmental contamination and chemicals and whatever else, that's one more thing that is off-putting. So, what other problems do we have? So obviously you're putting a mechanical shaft into a unit or a device that's pressurized with liquid. So you have to have shaft seals and bearings on this, here, so that the water does not leak out of the pump housing, of the water break housing. You also don't want air getting in there and causing air bubbles, which would impede the operation of the system. So you got to have really good shaft seals. So you got to have really good shaft seals at the top of a, say, 100, 200, 300-foot wind turbine tower that's exposed to the weather, some of the fiercest wind conditions. The reason you have this tower that height is to be exposed to the wind, but yet you're putting all this mechanical stuff up here. You have to make sure this shaft doesn't rust. You got to make sure your bearings don't get water in them and just get destroyed by corrosion and wear. Trying to do maintenance on this thing, so a guy's going to climb up this tower and do maintenance on this mechanical thing that's hundreds of feet in the air. If it was mine, I would not like doing that, especially because it's going to break in the wintertime on a windy day. That's just the Murphy's Law in action right there. Moving parts and fluid leaks. Those are disadvantages. The other thing is these pipes that are traveling up and down your wind turbine tower, they're carrying that precious heat that you spent all this effort to generate this heat. Then you're going to send it down pipes, and those pipes are basically like a big radiator. So you got to buy insulation and adequately insulate all of these hundreds of feet of tubing, assuming it's going to be like PEX tubing or something like that, to make sure you're not losing all your heat energy. And even with the best insulation, you can say you have a 3/4 or an inch diameter line going to your tower, you could have 3-4 inches of insulation on that, but you're still going to lose a lot of heat. And let's say the wind stops blowing and the water becomes static, and all that water in those lines, all the way from your house all the way up to the top of the tower, that water is going to go cold. And then when the wind starts blowing again, it's going to pump all that slug of cold water into your storage tank in your house for your heating system, and now you're going to be basically losing a lot of temperature. And there's ways that you can deal with that problem. You could have a control system down here that bypasses the water until the wind turbine gets that water heated back up. But that adds thermal lag to the system, and it adds more complexity. You got more parts down here, either electrical or mechanical, plumbing parts, valves, and things like that. So it's a big issue. And that's probably just a few of the reasons that this is not an ideal setup versus just using electricity. So let's just say that, all right, I've come to the conclusion that we're just going to use our wind turbine to generate electricity, which is what anybody in a sane state of mind would do for a lot of reasons. Okay, so we got our wind turbine. We're going to put our generator here. All right. So we got electrical generator. It's right here. We got our wires going down to the ground. Okay, your generator. It's basically some magnets and some coils of wire. You got two bearings. You know, the only really worrisome moving parts up here are your bearings. So you got to make sure you got good bearings that can hold up to the weather. Try to keep the moisture out of them. But other than that, you got some magnets, you got some coils of wire. You're generating probably 3-phase AC power. All right, that's what like your typical little residential wind turbine. They're either generating 3-phase and sending the 3-phase to the ground for you to deal with, or they have a rectifier built into the turbine that converts the 3-phase output of the generator into DC and sends the DC down. If it was mine, I'd prefer to have 3-phase in the tower coming down to the ground and then have my rectifier at ground level where it's more serviceable. The fewer parts that you have on this wind turbine tower, the better off you are. So I got 3 wires coming down, you know, phase A, B, and C, carrying electricity, alternating current. And that current's frequency varies with the wind speed. And the amount of power obviously varies with the wind speed. And I can run that into a rectifier, turn it into direct current, into DC. And here's where the real magic of electricity comes into play. So I don't care whether it's solar panels, photovoltaic panels, or wind turbines, or even hydroelectric turbines. There's what they call the maximum power point. Right? And your mechanical water break wind turbine will not be able to take advantage of this maximum power point. At least not without some kind of crazy water hydraulic controller or something like that. Theoretically, you could do it, but nobody in a sane state of mind intending to power their house or heat their house with wind energy would do it, because you can go out to go on the internet, go to wherever, and you can find an electronic controller that will actually operate your wind turbine at the maximum power point at all times. And what it does is it uses a little computer, a little microprocessor, to constantly measure the voltage and the current coming from the wind turbine. And it says, okay, I need more, can I get more power out of this machine? So it basically varies the impedance or the electrical resistance seen by the generator. And it adjusts that up and down dozens of times per second. And it says, okay, you know, actually in a solar panel, it's probably faster than a wind turbine because you got inertia here. But let's just say that every second it's looking for a new maximum power point. That computer constantly varies the mechanical load placed on the turbine. And it says, okay, I'm going to adjust the torque upwards and see if I can get more torque out of the wind. And it will do that. And if the value goes up, then it tries it again and again and again, and eventually you reach, so you got your voltage versus current curve. So voltage VI, and you know, you're going to end up with something like this, let's just say. And the maximum power point controller maintains that watt, this is watts, power, at the optimum level on the curve using a little computer. And It's all housed in a box, a few inches wide by a few inches tall. It's very small. And then it couples the output of that into your battery bank or your electrical resistance heater or whatever you're using to take the energy from the wind and put it to use in your building. So let's just say you have the simplest possible system, and that would be a maximum power point controller that takes the maximum power point from the wind turbine and just dumps it into a resistance heater and heats up water in a tank. You know, an 80-gallon water heater tank or whatever you have. And that tank then gets hotter and hotter and hotter, and it stores the energy. And that leads me to another advantage of electricity, is that water in that water heater tank can theoretically get as high a temperature as you want. The only thing that limits how hot that water can get is the temperature and pressure restrictions of the tank. So obviously if you heat it up to 400 degrees Fahrenheit, you're going to have a lot of pressure in the tank. But if the tank can hold it, then you can actually store the energy in that. Whereas with our wind turbine water break up on the tower, the hotter the water gets, the more losses you have. Whereas with electricity, the losses are effectively constant with water temperature. So it doesn't matter how that water could be 5 degrees or 100 degrees or whatever it might be, you know, just throwing out numbers. And the efficiency of converting the electricity into heat is the same. You're not losing more as you get hotter, like the way that you would with the hydromechanical system. So that's another advantage of using electricity for heating up your building or water or whatever it is using the wind. So you're reducing the maintenance that you're reducing the possibility for things breaking on the top of this tower. You're increasing the efficiency of the power transmission into the building, because you might lose, if you choose your voltage properly, you know, and you use a high enough voltage here, your losses to your building are single digits, like less than 5%. If you size the wires right, you could probably even get it less than 2% or 1%. You know, copper wire is relatively cheap, especially if you're comparing it to having to put in pipe and tube for moving liquid. You don't have to worry about the electricity leaking out of the thing and freezing and causing all kinds of damage. You don't have to put antifreeze in it. And then you get to use electronics to optimize the rotational speed of the wind turbine to get the most power out of that turbine based on the current conditions. So that's really where it really shines. And now this is all obviously talking about small wind turbines. A lot of the small wind turbines are set up where the rotor is a small enough diameter and the generators are sized such that if you short the generator, it effectively breaks the turbine. When I say break, I mean stops it from spinning in high winds. One of the big problems with wind is that as the wind speed increases, the power that you're getting out on the mechanical power that's coming out of the turbine increases with the cube, or it goes up cubed to the power of 3 versus wind speed. So if you double the wind speed, your power goes up by 8x. So if you have a 1 kilowatt wind turbine at 10 miles per hour, let's just say, at 20 miles per hour, now you have 8 kilowatts coming out of the wind turbine. That could be a big problem. So, you know, whether it's mechanical or electrical, you have to be able to deal with that issue. In the big utility scale systems, they basically have a maximum design wind speed that the thing can operate in, and then after that, they can actually change the pitch of these blades so that the wind is just kind of going through them and they aren't really putting a lot of force on the blades. There's also brakes in there that they can actually lock the rotor in place. Because those big wind turbines, if you get some kind of hurricane strength wind or something, they could destroy themselves very fast if there's not sufficient load on the shaft. So heating with the wind. Your best bet is turn the wind into electricity, send the electricity down wires into your building, and then make your choice of whether you want to just convert the electricity directly into heat using a resistance element, or even better, use that electricity to power a heat pump and then move the heat from outside to inside and basically double your return on your electricity invested, and really get a good bang for your buck out of your wind turbine. And if you grid tied your wind turbine, then you can take advantage of being able to shuffle power back and forth between the grid and the wind turbine to run your heater. And you can be effectively, almost energy independent, except for those dry wind days where you don't have a lot of wind, then you just rely on the grid. So that's that story. And it's just a very interesting sort of mechanical way that you can get heat from a wind turbine, or even a water turbine, a hydropower. You could even do this with liquid instead of air. It would be the same idea. But with hydropower, I would still convert to electricity, then convert to heat, rather than all this mechanical stuff. So this is very simple. The only thing where you have this so-called modern complexity is in the maximum power point controller. Other than that, we're talking 19th century technology here with the electric system. And that's it.